So we are going to go through our problem set 7 solutions today. So let's go ahead and get at it. So we're looking at the following diagram. It says representative volume per block of aluminum. So I know already that my Young's modulus for this kind of series of problems. I'm going to pull up this notebook as well. So aluminum, 69 gigapascals, 10 to the 9. I'm going to say my Poisson's ratio is equal to 0.3, approximately for metals. Good kind of rule of thumb. So good here. So we need to write out the full stress and strain tensors quantitatively. So I know this is my stress in the 3. I know this is my stress of 1. And then remember sigma ij. So we need to figure out what's the normal to the plane. So this is shearing like this. This is shearing like this. So what's happening here? So the normal would be sigma 3 and is pointing in the 1 direction. So sigma 3, 1. And what's the rotation? So it's going here. So the rotation would be like this. So around this axis, that's going to be counterclockwise. That's positive. So sigma 3, 1 equals sigma 1, 3 equals 15 kPa. So let's go ahead and write those out. So my stress, it's going to be, what's my 1, 1? So 96 times 10 to the 3, 0. And then what is it here? 15 times 10 to the 3. And then we have 0, 0, 0. And then we have sigma 3, 1, so 15 times 10 to the 3, 0. And then what's our sigma 3, 3? 26. So 26 times 10 to the 3. And here we go. So let's look at that stress slash matrix form. There we go. That's our stress tensor quantitatively in pascals. So now we need to write out the strain tensor. Well, we know we're going to use this equation, epsilon ij equals E times plus nu times sigma j minus nu sigma kk delta j. Kronecker delta. We've gone through this guy before. So let's go ahead and write it out. So I know I'm going to have a strain in the 1, 1 direction. So let's go ahead. I've got strain in 1, 1, and that's going to be equal to 1 divided by y times, I'm going to actually define here, sigma 1 equals stress 1, 1. Let's go ahead. My sig 2, 2 equals stress 2, 2. And my sig 3, 3 equals stress 3, 3. And my sig 1, 3 equals stress 1, 3. There we go. So I know my epsilon 1, 1 is going to be basically 1 over y times sig 1, 1 minus nu times sig 2, 2 plus sig 3, 3. So I know that from that equation. So I've got that here. Let's go ahead and put this here for 2, 2, 2, 2, and then turns out to 1, 1. E3, 3 is equal to same thing. Let's kind of push this out here. E3, 3. E3, 3, sig 1, 1. I'm going to do sig 2, 2. And there we go right there. And then the last one we need to kind of think about is the following. So we need to kind of take a little bit of a peek at the following answer. So let's go ahead and let's work that one out right there. One quick second here. Just checking out another problem on this. So let's do our epsilon 1, 3. So if we are writing here, epsilon 3 is just going to be 1 over e times 1 plus nu times 1 plus nu times sigma 1, 3. So let's go ahead and write that one out. So E1, 3 is going to be equal to 1 divided by y times 1 plus nu times sig 1, 3. And there we go. That's it. So looking at those values, we're all good to go here. So we have, let's see what problems we've answered. So now you could kind of, these are the only strain components in my strain tensor. So finish 1, finish 2. Now we're asked to calculate the rotation to get the principal stress state and a lot of these other values. So let's go ahead and let's write out that stress state. So our stress state is going to be basically 96. So I'm going to put this out. So my stress tensor looks like the following. So 96, 0, and what is it here? 26, and then 15. 15, 0, 0, 0, 15, 0, right here. Let's make sure I'm right. Yep, we're good to go. So let's look at each of these planes independently, because we're going to have to draw the Mohr circle and we're going to have to do some action with it. So this is going to be my 2 plane. So look at my Mohr circle here. I've got my green is going to be my 2, 3 plane. So 2, 3, like this. And then I'm going to have my this guy, this guy, this guy, and this guy. That's going to be my 1, 3 plane right over here. So let's draw our Mohr circle in 1, 2, and 2, 3. This is going to be pretty easy. It's just 96. This is going to be 0. That's my Mohr circle. So I'm already in my principal stress state. So 0 rotation to get to principal. To get to my maximum shear, that's going to be 45 degrees. And then the problem is also asking us calculate the rotation to get to the principal stress state for the 1, 2. So we did that. Write the stress state for each plane for a rotation 34 degrees clockwise from the maximum shear stress state. So we know in real space we had to go 45. In Mohr circle it's 2 theta. So we know that in real space it's 45. So we went here counterclockwise, 45 from our original stress state here to get to our maximum shear here. So we did 45 clockwise. Now we're asked to go 34 counterclockwise. So I need to find out what's my new stress state at an angle of 45 minus 34. So I could do that pretty straightforward. So let's go ahead and let's bring this over here to the side. I'm just going to do T dot, I'm going to do my kind of my stress tensor here. So I know that I've got 96, 0, and 0, because those are my values, slash dot theta goes to 45 minus 34. And let's look at this. Voila. Now, let's also kind of do this basically mathematically. You can kind of do this as well, because we know that basically we're going to have this circle, right? We actually already have the values here. So we have this circle. And so what we're really doing is we're going 45 minus 34. So what's my, basically I'm left here with an angle in the kind of the real, you could do kind of the 2 theta space, but again, we'll do the linear algebra approach. You can do the same exact thing essentially with 2 theta as well. So we know here that this resultant, the final angle is going to be a theta of 45 minus 34. So we can actually do that right here. So 45 minus 34, so 11. So really, I'm looking at kind of what is my, I know the center here. So I'm going to be looking at this kind of stress state where my 2 theta, this angle here is going to be, I know that this is R. So I'm looking at a right triangle essentially where I have R and I know my 2 theta. And so now I have to figure out what are, I know this point here, it's the center of my circle. So it's going to be 96 divided by 2. So 96 divided by 2. So I can go ahead and figure out what those rest of those values are. Let's go ahead and do that just to kind of double check our answer. So all right, so if we know that the 2 theta is going to be twice this, so I need to solve. So I know that here, again, sine 2 theta equals, x over r, opposite over hypotenuse. So I need to solve sine of 2 times 11 degree equals x divided by my radius, which is going to be 96 divided by 2. Solve for x. Solve for that numerically. And so my x value is going to be that 17.981. So you see, it's the exact same value. Now, why is it negative? Because we're looking essentially, again, we're going to have circular symmetry, so it's going to be at the bottom here. So we've got that one value there. Excellent. What about this y value? I need to do my cosine, right? So let's do the same exact thing, but for cosine, we'll see, we'll get the same. Okay, very similar. Cosine, 44. So it's 44. Again, let's look. Go ahead and calculate that out. So it's 44 from my center of my circle plus 96 divided by 2. What do you know? Right here. And if it's on the other side, it would be subtract minus, right? So it'd be the same thing here, and it'd be minus. Same thing. Same exact thing, except 96 anyways, divided. We would have it over here. So that has to be positive. It's not going to be negative because we have to pull it over here. Minus 3. There we go. 92, 3.4, 17. We got it. So, but you see how, why would I do that, all that geometry, when I could just use my linear algebra approach, as long as I know my, essentially how to kind of work through those angles. So that's the stress state there. I could do the exact same thing for 2, 3, exact same process. So I've got 26, I've got 0, that's my circle. So I know I'm already in the principal stress state, so 0-degree rotation there. I need to do a 90-degree rotation in 2 theta space, so that's a 45-degree rotation. And if I want the stress state, I mean, you see I'm kind of answering this question as well to get to how to get to the maximum stress state. So if I do T dot, I've got 26, I've got 0, 0. Here, actually I've got, we kind of keep it in the same notation. You get to do this 0, 26, 0, and then slash dot theta goes to, again, 45 minus 34, and that's going to be my stress state right here. Bang. And you could do the same check there. Now, what about 1, 3? There always has to be a hard one, right? So we have 96, we have 26, we also have 15, 15. So I need to figure out first, I'm going to have 4 points. So I'm initially not in my principal stress state. So I need to figure out what's this 2 theta to get to my principal stress state. What is that rotation? Well, I can do that pretty straightforward. So I could do, I know that, for example, this point is going to be, I'm a 96. I have a, if I look at my kind of, I've got a 26 and I've got 15. That's my sigma 1, or basically my sigma 1, 1, my sigma 3, 3, and my sigma 1, 3. And I want to solve, let's solve at what angle solved when this, let's do the whole thing. I want to solve, to get to my principal stress rate, I know this is going to give me 3 equations when I multiply this. So I have 3 equations in here. 1 equation here, 2 equation here, again, because I'm calculating, I'm dotting it to get this shear stress. So I know I'm in my principal stress state when I'm not, when that shear is equal to 0. So I set this equal to 0, solve for theta, and let's do this numerically, and voila. So I'm going to pick the smallest value because I want to kind of assume that we are looking in this kind of state here. So that's my angle in real space. So that's the angle to get to the principal stress state. So I need to rotate basically clockwise this amount to get to my principal stress state. Well, I know then that if I do 2 times this, like the rotation to get to my from the principal is 45. If I have to just go from there the other way, I know that, okay, this is the angle to get to my principal stress state. What's the angle to get to my maximum shear stress state? It's just going to be here to here. So that's the rotation I have to do clockwise to get to that stress state. And then now, if I want to go from here, so that's the rotation from essentially here, I need to rotate that 33 degrees this way to get to my maximum shear. So from my original stress state to here, I have to do that rotation. And then from there, I have to do another 34 degrees clockwise rotation. So that's going to give me this. And so I could do the same exact thing. So now I could just do T dot this original stress state right here. And then that's going to give me this expression. So let's look at, come on, let's solve that guy numerically. Oh, I need to do slash dot theta goes to that. There it is. So again, I need to first, for this one, we found that that theta is equal to 11 degrees. So I need to rotate clockwise 11 degrees, essentially, what we found, it's a little bit different. So I need to rotate 11 degrees here to get to my principal stress state. I need to rotate basically 45 minus this in the, I need to rotate 33 degrees counterclockwise to get to my maximum shear. And then from that maximum shear, I need to rotate 34 opposite there. So that's the rotation I have to, and this is why the linear algebra approach is so nice, right? I don't have to kind of think about all these different angles and just kind of plug and go. So excellent. So we've answered 3 and 4 simultaneously. What's the full principal stress tensor? I could just do my eigenvalues, or again, I could look at my, from that angle here, I could kind of solve, like for example, I could go look at my, what are my sigma 1, sigma 2, sigma 3s? I could just look at this. So you can see this is essentially 0. So this sigma 1 is the largest, and then this sigma 2 is the largest, and then the last value will be 0. But I could do the exact same eigenvalues of stress. I could look at this numerically. And what do you know? we get essentially, again, this is, these all need to be multiplied by, these are in kilopascals, so we should be multiplying them out. But again, this is just for kind of illustration purposes. But yeah, same exact values. There you go. All right. Number 6, the more important problems that you'll kind of see. So trash bags are commonly made of polyethylene. So polyethylene is a polymer, so I know my Young's modulus equal to 1 times 10 Pascal. My Poisson's ratio is 0.4. And I'm basically pushing down on my polyethylene a square, on basically a square mold. So I'm just kind of pushing in here. I want to define my coordinate system. So I clearly have a stress in the 3,3 direction. There's no kind of constraint otherwise. So when I'm looking at my strain tensor, so my stress tensor just looks like this, 0, 0, 0, because we're saying essentially the mold is well lubricated, so no friction, so no, essentially we're not going to have any of these shear stresses. So I'm going to have 0, 0, 0, 0, 0, sigma 3. So I'm going to have some sigma 3,3. In my strain tensor, I'm going to have a strain 1, 1, because when I push down on it, it's going to expand on these other directions. So I'm strain 1, 1, strain 2, 2, and I'm going to have a negative compressive strain here. That's it. So the initial thickness of our material is this. We need to reduce it to 50 micrometers. So I know that the strain in the 3,3, because that's what we're reducing the thickness, is going to be the change in L, or thickness, over L naught, which is going to be our final thickness is going to be 50 times 10 to the minus 6 minus my initial thickness, which is 0.1, divided by my initial thickness. So let's go ahead and define some of these things right now. So I'm going to go ahead and quit my kernel. Quit it, local. I'm going to make a separate section here, Alt 6, or Alt 4, problem 6. So y is equal to 1 times 10 to the 9th. Mu is equal to 0.4. And I know that my E33 is equal to, what is it? Basically 50 times 10 to the minus 6 final length minus initial length, 0.1, divided by that initial length. There you go. And then we can kind of start to solve what's our knowns and what's our unknowns. So we know our sigma 3,3. We don't know this, we don't know this, and we don't know this. But luckily I have 3 equations, and I'm going to solve for those 3 unknowns. I'm going to solve and say that my E11 equals 1 over y times basically my sig11. So we know that is 0. Sig11 equals 0. Sig22 equals 0. But my sig33 is alive and well. So sig11 minus mu times sig22 plus sig33. I'm going to do the exact same thing. I'm not going to do a squiggly bracket here. I'm going to solve for all of these simultaneously. And then I'm going to solve for my E11, my E22, and my sig33. So I need to change these to 2. I need to do this to 2. I need this to be 1, I need this to be 3, I need this to be 3, and I need this to be 1. And with that, I can close that up, solve for it, and kind of makes sense. Look at compressive stress, positive stress, or positive strain, because they're expanding. Looks good. Draw the full Mohr circle space. We're already in our Mohr circle, so our Mohr circle looks like this, tau sigma. It'd just be sigma 3, and all the rest of these are 0. That's our 3D Mohr circle. So what's the rotation to get the principal stress? We're already in there. We're lying straight right here. We only have basically normal stresses. To maximum shear, it's just going to be 45. Awesome. Now, finally, I'm making a new stent material out of polymer that will be used to inflate blood vessels as seen below. So to inflate an artery, avoid a cardiac stress, the stent must be 100 nanometers thick. So my P is equal to 100 nanometers. Again, it says right here, we're also saying polymer. So P equals 9th, mu is equal to 0.4. So my diameter, D, is equal to 6. So my radius equals 3 micrometers. So when I ever do this, so I'll also draw kind of a coordinate system here. I'm going to call this 1, this 2. So radius, thickness, diameter, thickness. I'm going to quit the kernel here. I know I need to look at thin-walled pressure vessels. So Alt 4, so 7. So let's go ahead and get into this. So my radius is equal to 3 times 10 to the minus 6 my thickness is equal to 100 times 10 to the minus 9. And I need to see if my radius over thickness is greater than 10. Then I'm in a thin wall pressure vessel case. And let's go ahead and check that out. So R divided by T. Oh yeah. So once I know that, I can jump immediately into this expression. So I know that my 1, is my longitudinal, my 2, is my hoop, here, 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 here. And then I also know that my sigma hoop is equal to delta P R over T. My sigma L is equal to sigma H divided by 2. And it says right here that typically a stent must be inflated with at least 10 atm of pressure. So my delta P is equal to 10 times 101,325 in pascals. So 10, 101,325. Yep, looks good, pretty good to me. Let me just double check that. All right. So we know our delta P, we know our R, we know T, we know delta P, and then we also know that my epsilon H equals 1 E times sigma H minus mu sigma L, and my L is equal to 1 E times sigma L minus mu sigma H. So let's go ahead. We can solve for everything here directly. So we don't have to worry too much about it. So my sig H equals del P times R divided by T. My sig L equals sig H divided by 2. My EH equals 1 divided by Y times sig H. Oops. Oh, I need to define my Y. Y is equal to 1 times 10 to the 9. My nu is equal to 0.4. So 1 over Y times sig H minus mu times sig L. My EL is equal to 1 over Y times sig L minus mu times sig H. And we can go ahead and shift under those guys, and then we're sitting pretty. So let's go ahead, knock that one out. There we go. That's our full stress tensor. What's the rotation to get to principal stress? We're already in principal stress state. Maximum shear, that's going to be 45 degrees. We have that as well. We're at the principal stress tensor for the stress state. We already are in that stress state. So sigma H, sigma L, everything else is 0. That's it. So my stress tensor is already in that principal stress state. And if you were to draw the molar circle, it would just look like this for any thin wall pressure vessel. Sigma H, sigma L, 0. This. We are good to go. So I hope that was we went through it pretty quick, but hopefully it kind of clarifies any questions you may have had. And then, yeah, good luck, and I'll see you on the next problem set and then on the exam. And then we're done with the ENGR 110. Thanks. See you next time.